The next presenter that we've got is Dr. Sylvia Salgar-Chaparro, and she's an academic researcher at the Curtin Corrosion Centre in Curtin University, and that's over in the west of Australia. So that's, I think it's about 4,000 kilometres away from where I am today, despite still being in Australia. She's a biologist with a PhD in chemical engineering and has over 15 years of experience in MIC, molecular biology and microbial ecology. She works closely with industry partners in the oil and gas, mining, maritime and healthcare sectors to address complex MIC challenges. I will stop sharing my slides, Sylvia, and if you can start sharing yours whenever you're ready.
Okay.
I can see those, all good to go.
Perfect. Thank you, Scott. Thank you for organizing this webinar. Good afternoon or good morning, everyone, wherever you are. Thank you for joining us today. So I'm going to talk about MIC in oil and gas systems. When we talk about MIC in these systems, it is very important to consider the nature of the system itself. Oil and gas systems are not simple environments. They are complex engineered process systems. So the produced fluids come from subsurface reservoirs, and they have to travel over long distances through different equipment, including tanks, separators, pipelines. So over this long journey, the fluids experience different changes in temperature and pressure, even in the chemistry of the fluid itself. So from a microbiological perspective, this represents a highly dynamic environment, and microorganisms living in these production fluids, they have to tolerate these extreme conditions that would come with the system. So they have to survive to high salinity, high pressures, high temperatures, and even the exposure to several chemicals, including the treatment chemicals such as corrosion inhibitors, oxygen scavengers, and in many cases, they can also survive to the biocides. So despite these harsh conditions, microorganisms not only survive, but actually they can adapt and proliferate in these environments, causing several issues. There are three known phenomena known to be caused by microorganisms in these systems, and these include the reservoir souring due to the production of H2S, clogging of filters due to biofilm growth, and also corrosion, which is the topic of this webinar. So I would like to say that microorganisms not only induce internal corrosion in these facilities, but they can also induce or influence external corrosion processes, as there are also microorganisms living in the environments where the facilities are located. And it's also important to mention that in oil and gas industry, it's very common to use carbon steel or mild steels, which are steels that are more susceptible to the corrosion phenomenon. And therefore is why MIC is a significant threat of these systems. So in this slide, I am presenting three of the major events that occur due to the action of microorganisms in oil and gas facilities. In my first example, occurred in 1977, and it happened in Qatar. It was a failure of a propane tank containing 236,000 barrels of this propane, which were released and ignite, causing the death of several people. So after investigation analysis, they find out that it was due to localized corrosion in the welded regions, and it was consistent with an MIC mechanism. Basically, there was a hydro test in the tank months ago, and there was seawater remaining from this hydro test. So microorganisms that come with the seawater contaminated the surface of the tanks, and they caused this event. In my second example is an oil spill that occurred in 2006 in the Alaska North Slope. 267,000 gallons of crude oil were released to the environment, contaminated more than 7,000 square meters of pristine land. In this failure, it was understood that it was an internal corrosion problem due to a hole in a pipeline, and this one was due to the action of sulfate-reducing bacteria that were growing on the surface. And the most recent example occurred in 2015. It was a release of more than 100,000 tons of gas, methane, and ethane in the Alicio Canyon. And in this case, it was a rupture of the well casing due to external corrosion problems. So we can see that MIC actually represents a significant operational safety and environmental risk for oil and gas operation, and therefore it's very important to prevent these events from happening. So oil and gas operators normally use structured programs based on risk assessment just to manage the risk of different corrosion threats, including MIC. And normally this process comes as a feedback loop of 3 stages of assessment, mitigation, and monitoring. So this assessment step is very critical to identify the risk of the facility to experience any corrosion phenomenon, including MIC. And the risk at the end is the result of the livelihood by the consequence. So in the case of MIC, it is important to collect samples to get information of the microbial communities living in the facility. So for this one, we can collect fluid samples to get information from the planktonic communities. But most importantly, we will need to collect information from the microorganisms that are able to attach to the metal surface, so the SSI community. And there are several methods available that we can get different pieces of information about the microbial community. We can get the cell numbers, the activity level, and even the microbial composition using the latest molecular tools. But it's very important to highlight that no single method can directly predict the corrosion severity or the likelihood of MIC. And this is because, as Scott mentioned at the beginning, at the end, MIC result from the interaction of these 3 different factors, not just the microorganisms, but actually what is in the environment for them to behave in a corrosive manner, and also what are the material characteristics and the susceptibility of the material to get affected by the action of the microorganisms. So therefore, at the NMIC, despite we know what is causing the issue, is very difficult to manage because it's somehow difficult to understand how the interaction of these 3 different factors will result in a likelihood of MIC. And it's also important to mention that it happened many times that you get reports from oil fields where you get contradictory field observations. So that there are many reports where fields have pretty high number of cells and they don't have any MIC issues at all, but there are fields that have low number of cells and very severe or many issues with MIC. So it's here where the interconnection of the different factors play a role, and that combined effect is important to be assessed. And this has been the focus of my research of the last 10 years. I have been looking at different environmental changes that can happen in oil and gas facilities to study the effect on the community and the effect on the data preparation on the method. And here today I am presenting briefly the results of 2 of these studies. In the first one, I was looking at the effect of temperature gradients in production pipelines. This is a very common phenomenon in oil and gas systems because when the fluid comes from the reservoir, it normally comes at a higher temperature. But once it reaches the surface, well, it starts to cool down to get balanced with the environmental temperature. So there is a gradient over the transportation process. So I wanted to know what happened with this gradient, if the microorganisms that are commonly living in higher temperature will get dormant, or what will happen with them once the temperature of the fluid reduce. So for this, I collected samples from an Australian FPSO where the reservoir fluid comes at 60 degrees, but when it reaches the separators, it comes at 40 degrees. So I set up 2 bioreactors, one at 40 degrees and the other at 60 degrees, and I used the same solution in both reactors and the same inoculum from the Australian FPSO. So I wanted to know what happened over carbonate steel coupons that were immersed in this bioreactor. So I look at the microbial community that developed after a couple of weeks of immersion. And this graph on the right is actually talking about the microbial community composition. And just from the color scheme that you can see clear differences in the color pattern. So each color is represented and different species. So the biofilm that I formed in the 2 conditions was composed of different microorganisms. But I want to also highlight that at the end, both reactors still have the same metabolic function. So microorganisms that live in both reactors were related to methanogens, acid-producing bacteria, sulfate-reducing bacteria, and disulfide-reducing bacteria. So all these metabolic capabilities were present in both conditions. Then I look at the microbial concentration and the activity numbers of the biofilms, and then I can see clear differences. So at 40 degrees, there is an increase in the number of cells and the activity level, which at the end resulted in a higher localized corrosion rate triggered by this microbial community, which was more than double the corrosion rate triggered by the community living at 60 degrees. So in this specific case, as fluids cool along the production pipeline, the microbial activity increases and the corrosion risk becomes more severe in this condition. In my second example, I was looking at the effect of different fluid chemistries, and this also happened very common because the production systems, when they go to the processing facility, well, they receive fluids from different reservoirs or different wells that may have different chemistry. So in my study, I wanted to know what happened again with the microbial communities and the corrosion rates. I have three different conditions in this case. I wanted to have produce water without sulfur compounds, and also produce water having sulfate or thiosulfate, which has been found out here in Australia that thiosulfate-reducing bacteria are very common in oil and gas systems, normally the ones at higher temperature, and they can cause significant issues. So again, I inoculated my two reactors with the same microbial community, but when I look at the microbial composition again, the conditions of the chemistry in the system was making that my microbial community have different composition. So different species were developing in the three biofilms, but again, I have the same metabolic capabilities I had in my previous study. Then when I look at the microbial concentration, I can see that the no sulfur condition was the one presenting the highest number of cells, one order of magnitude higher compared to the sulfate and the thiosulfate condition. However, and very interesting is that when we look at the microbial activity level, this one doesn't correlate with the cell numbers. So in the condition I had more bacteria, I had the less activity level, and at the end I got the insignificant localized corrosion rate compared to the other two conditions. And this is a clear example. What happened in fields is that not every time there is a direct or direct correlation of the cell concentration and the corrosion rate. And this is where MIC livelihood become very challenging for oil and gas operators. As Scott mentioned as well, microorganisms in this oil and gas system not only trigger a corrosion mechanism, but they can also come and accelerate corrosion rates triggered by other factors. And it's very common to observe this in crevice corrosion and deposit corrosion. So it seems to have a synergistic effect when microorganisms colonize these sections affected by other mechanisms. It seems they can affect the kinetics of the reactions, and most of the time they make it worse. So in oil and gas system, it is likely to have multiple corrosion mechanisms happening at the same time. So then the question was, well, what or how we use the information generated during the research or in the academia, and how this can be translated to the industry. And this has been the focus of my research in the latest year. We have a joint industry project with oil and gas partners. And in this one, we identify that they can get different pieces of information during the assessment, but they don't know how to integrate the data to at the end have a likelihood of MIC. So we'll start working on a probabilistic framework that can integrate operational, chemical, and microbiological evidence, and that can help oil and gas operators to predict the risk of MIC in their systems. So at the beginning, we developed a conceptual network on interconnection of different factors, including chemistry of the fluid, biological parameters, and also operational conditions. And then we work over 2 years in building a database of field information from the oil and gas operators participating in the joint industry project, and also collecting information for databases or publicly available in websites. So we got a database of more than 4,500 data points. With this database, we were able to train models using data scientists and artificial intelligence tools to actually get the probability of biofilm formation and the probability of MIC damage. So these models were validated in the desktop, like they were mathematically validated. But we have recently received a grant from the Australian Economic Accelerator to get this model to the next level, which means to the prototype level, where this one will be tested in the oil and gas systems to get the further validation. It's very specific for carbon steel systems and oil and gas facilities. So with this, I come to the end of my presentation. I just have a slide summarizing the key points I have presented today. So basically, MIC represents a significant threat to the asset integrity in oil and gas system, but this one is not just driven by microorganisms. They actually interact with the conditions of the environment, and this is what results the livelihood of MIC. Therefore, just looking at the activity level of the cell numbers is not going to give us the livelihood of MIC in any oil and gas system. We need to look at the interconnection of the factors. And that is important also to consider that they can come to coexist with other corrosion processes. So it's also important to consider this when assessing the risk of MIC. And finally, that there are many tools available to can actually integrate different data, like the probabilistic models, and this can actually help industry operators to predict the likelihood of MIC. Thank you, everyone. I'm happy to answer questions at the end of the webinar.
That's great, Sylvia. Thank you very much. Some very interesting work there. I'm sure we'll get some back to some Q&A at the end.